Some final comments on the SAR IDC design. So let's take a look at it. So how to test the NLs and DNLs? Have you thought about it? In simulation, it's actually pretty simple. If you look at this one, I mean, the quality of the images are really low from the student here. I think these groups are, graduate students in Columbia University, and they did a 1 year long project and laid it out in, is that IBM 130 nanometer technology, and taped it out. So we appreciate the design, and they post everything on the website, but the quality is very low. So when you are looking at the simulation results, they can actually do a better resolution figure, right? They just didn't. Anyway, so if you look at this one, this is a DC sweep to test our ADC. Can we use this technique to find out the NLs and DNLs? Do you still remember how did we calculate them? There's a line and a stars, right? That's how we get them. The same concept. When in the simulation, you want to do the same thing. But how can we do it? How can we get the two curves over here on the simulation? So first, what are these? So what's the straight line over here, the linear? Analog input. So the analog input can be a sine wave. That's why we are trying to mimic the real situation in the real world. The input signal can be any AC swing, right? The thing is, all the AC signals are, all the points on the signals, they're just voltage signals. And if we just use a linear DC sweep, so we can actually feed any possible input voltage to the input of the ADC, right? You just do a DC sweep. That's the whole range. No other possible input voltages will be showing up in there. Already, explore all the input voltages. So that's why you can see the stars. So where you are getting the stars. Where? The output or the one just after the SAR block? Everywhere. Yeah. So the right one, the right line, the red stars, they are the output from the DAC. And the DAC is where? Where is the DAC? Remember that? Connect to the output of, no. Think it one more time. This guy, right? Connect to the, we just name it as a door 8-bit door register. So what's in there? What's in there? We have a quiz today, you know that. So 20 minutes before the end of the class, regarding all the little questions, little things about the SAR IDC. Did you prepare that? So I think on Wednesday. Is it Friday? All right. So on Wednesday we talk about it. I mean, how do we want to prepare for the quiz? I know it's already late. You don't have a chance to prepare that anymore. But did I talk about that? I mean, how we want to prepare for the quiz on Friday? Watch the lecture video, right? And if you can, I already provided all the simulation files here. Just simulate it so you can understand the whole structure. Very simple concepts, just 4 questions, very fundamental. Okay, so this, what's in there? Where are the counters? Here. right? So trying to do the timing, so you can send the commands, the correct commands to the circuit at the correct time. So what's in here? 8-bit register, just different flops, right? 8-bit. So I will give you several options, right? Are they parallel in, parallel out, or serial in, parallel out, or parallel in, serial out, or something else? Tongue twister. There are several types of shift registers. Remember, if you have learned that in logic, so definitely you learn, but probably forgot about that, which is fine. I mean, just asking when you're looking at the structure, is that serial in, parallel out, or parallel in, parallel out, or parallel in, serial out? Yeah, parallel in, parallel out. You got 8-bit for the input and 8-bit for the output. So the 8-bit register is not doing anything else but just as a latch, right? So whenever, or like a switch, whenever you want to send the signal out to the DAC, you just turn it on, right? Just like it's parallel in, parallel out. So when you are going to use a parallel in, serial out, and why? They're all digital. So when you are getting, so this looks like a parallel in, serial out, but it's not serial. It's digital in, analog out. So when I'm talking about parallel in, serial out, it's all digital, parallel digital, and serial digital out, right? They're just one and zeros. It's not a continuous output like an analog voltage for VL. So when do you need that parallel in, serial out? It's actually everywhere. Hmm? Mm-mm. Kind of, right? It's a parallel in, but you know what I'm talking about is parallel in, serial out is very important, because if you grab an ADC, you can buy it off the shelf, right? You can buy a lot of ADC like the ENGR338, right? So that for microchip. So it has a SPI interface, 4 pins, and but only two. So one is for power, one is for clock, right? So this is a clock. This is for power, and you got in and out. So it's a DAC. So it shouldn't be that one. I forgot the name, but anyway, so it's a DAC or ADC. ADC, okay? So analog in. So there will be a circuit very similar to ours. So internally, it's going to convert the analog signal into a parallel output, right? So internally, you're not seeing that. But internally, for example, there's a block. It really does that, ADC. So you're getting a parallel output over here in a digital form, right? However, you got an in and out here for just like 2 pins for communication with a microcontroller like Arduino or so, And you got another SPI interface over here to do that communication. I mean, how to convert this one to here? Yeah, it's parallel in, serial out. So whenever the data here at the same time shows up, so all the digital voltages like 1 zeros being converted, it's done here. This should be after the door clock, right? The door register is only sending the valid digital numbers, results, right? So whenever it shows a digital combination here at one time period or at one moment, you have to convert it into a serial output. So serial means, for example, it's a 1001, like, so this is 01, 00, 1, 1, 0, okay? And it has to be done in that way because there are 8 pins in parallel, and you have to send everything to a register and then pump them out one by one. So you are getting a serial output, not parallel. So why do we want a serial output instead of parallel output? Yeah, it's taking a lot of pin resource on the board, taking a lot of space. So you prefer to reduce the number of the pins. So SPI is one of them. There's another one called I2C, just one wire. Actually, two wires. One is for clock, one is for data. And there's a temperature sensor called from Dallas Semiconductors. It's a temperature sensor, and it's called a one-wire temp sensor. It's a special I2C protocol, and it's just a power and a ground. So it's VDD, GND, and a signal. There's not even a clock. How that works? So only one pin, and it's digital. Think about it. That's awesome. In the past, there are some other temperature sensors like thermistors, right? It's a register that senses temperature and changes resistance. So if you have a voltage divider here, here's a VL. So you can detecting the variation of the resistance by detecting VL to find out the resistance. There will be an equation to calculate it. So the drawback of this one is very cheap, right? So you can buy $1 you can buy probably 20 of them. Temperature sensors, it's pretty good actually. Not that accurate, but very cheap, very small. So for this type of temperature sensor, it's getting an analog VL, and what you need to read it as a temperature. You need ADC. It's an analog voltage. You need ADC to convert it and then do the calculation, right? And then convert it into the digital signal. So you can, you need the whole ADC to do it. So what about this one wire? This Dallas, is that like 1820? I forgot the name. It's probably this. I did a project for the Pagosa Springs, the hot tubs, for sensing the temperature of the water in there. So this one, they already have. If you imagine that, if you just look at the pin, it's sending all the digital signals to this one pin. So what's happening inside? Yeah, we are not considering the clock. I mean, it's sending digital signals, and you have to interface it with the microcontroller. So the microcontroller can sense that signal. So you have to write a library to it. But anyway, whenever the digital shows up, you can just read it, right? So read it. Just a different protocol. You don't really have a clock because it's by default. It's able to. It's just more intelligent. That's why sometimes when the device is super simple to use, it's actually designed by the top engineers. So I was thinking about this yesterday. I mean, what are the three levels of engineers? Think about. So most of us are beginners. And the top engineers are the ones who can make really complicated stuff very simple to use. And the one second to the top one is the ones can make really simple stuff very complicated. I mean, do you have any examples? I mean, for the people who design this one, they're the top engineers who can make really complicated stuff very simple to use. It's one wire and hook it up to an MCU, digital data, you can read it very easily. For the ones who can make really simple things that very complicated is like what we are trying to do. I mean, we're not there yet, but you can buy an ADC, off-the-shelf ADC by $2, and we're designing the ADC ourselves. So we're making a very simple thing very complicated, right? If you can make it work, we'll be able to connect the IDC to a lot of digital interfaces and put them together and then connect to a CPU core. So that's the year 3 plan. And eventually we can get Arduino, like MCU for system on chip like Arduino. Not as good as Arduino, but it's going to be a microcontroller. So we're going to design the microcontroller eventually. But you can buy an Arduino microcontroller for $30. So we're trying to become the second to the best. All right. So what's happening inside, you can imagine, it must have a very simple temperature sensor, which can convert temperature into analog voltages. And then it must have an ADC to digitize that analog voltage into a digital signal, and then do the the parallel to serial. There must be a digital block over there to do that job. Is able to send every single bit in a serial in just one wire instead of 8 or 10 parallel wires. It just integrates everything inside. You don't have to do all this digital analog conversion and also the parallel to serial conversion by itself. So that's what's happening for this temperature sensor. Right? So most of you guys are in my 351, so you are going to have a chance to work with these temperature sensors. They are really, really awesome. Okay, let's come back to here. Parallel in, parallel out for the DAC. So that's why we can convert the parallel output into one wire, so we can probe it. Right? It's not just in LT-SPICE, but also in the real world. If you have to use a digital analyzer, you are having multiple parallel digital pins, and you have to use a cursor to look at what are these digital values and convert it into an analog value. So why not just use a DAC? It's just going to show you that you can just use one probe to probe that voltage, right? So you can show it in either in LT-SPICE or in a oscilloscope in the lab. So that's why for this one, I just directly copied it from this website, right? This is the same figure. You couldn't even read what are these values, right? Anyway, so it's a DC sweep. So I think in one of the labs at the very beginning of the semester, you did a DC sweep, did you? It's a dot DC and the voltage source from 0 to 5 and things like that. Just feed that voltage into your ADC and probe the DAC, the output of the DAC, to show the stars. And there's one thing you have to do, which I think I did it 10 years ago after I forgot how to do it. So all the data points are being plotted in LT-SPICE, right? So there should be a way to extract the raw data and plot it in MATLAB so you can process it. Otherwise, it just shows up in the LT-SPICE. You couldn't modify it. It's going to extract the data and then save it in like either .txt form or .dat form or any type of txt or data file and load it into MATLAB and do the calculation so you can get all the points, right? So you can find out all the points. It's just like a matrix, but it's one dimension, like a vector. And you need to know like where you want to, what are the points you want to use to calculate DNLs and NLs. What are these, for example? Yeah, I think at the rising edge here, right? I haven't done that yet. I'm just thinking like, whatever you think is right, we should do it. So remember when we are doing the hand calculation for the DNLs and NLs, we're just looking at the points, right, of the input. No, the input here, and then see what's the real step is over here. That's for DNLs. For NLs, you are looking at the absolute value of these points, right? I mean, it's doable, right? You just need to know how to load the raw data into MATLAB. And so what's the way to find out this rising edge in MATLAB? You have a bunch of points in there. Say it again. Yeah, how do we, because you have two vectors there, right? One is a DC sweep line of the linear voltage points. Another one is a right line, which are stars, like these ones. So you want to do subtraction for some of the points to find out DNLs, right? There will be a very simple signal processing technique over there. You guys are creative, right? Just do it and let me know. Can you were in 104, in your 104 or some other MATLAB or Python, whatever you want to use. Okay. Okay, a few questions or tasks. First, duplicate the work in electrical VLSI and make it clean and neat so other people can directly use your schematics for layouts. And also you have to, because we talked about that on Wednesday regarding the timing circuit. Because I think this should be 10, right? Not 9. Please try it and let me know. Let's show the results on your report. And that's where it is, right? So use 10 instead of 9. Show the results. And let's use C5. So C5 is the only one available for electrical VLSI. So I have to use C5, which is 5 volts. The design you can download from my website is 1 volt. You must increase simulation results and the discussions of each function block to receive credits. It must be DRC clean. Okay, shouldn't have any errors. And answer the questions in section 7A. So what are these questions? I think I already answered a lot of these questions on Wednesday. So why they are different, right? Second, does this matter? This dip, does that matter? And okay, what are the INL-DNLs? Okay. Any questions regarding the project? You want to start working on that as soon as you can. Okay, it's a lot of work in there. You also have the ALU lab. It's a lot of very tedious wiring stuff over there. But you won't do that for many times. You just have to do it once at least, I think. Okay. Here? Yeah, forgot. Look at the plan a little quick. What's the schedule for the rest of the semester? So today we are actually not doing any memory circuit. We're going to wrap up. We have done that, and there will be a little remaining stuff for the digital model for the circuit design. And I'll start the discussion of memory circuits next week. And no lectures here, so we can have time to work on the project. Okay. We have 10 minutes. I'll give you 20 minutes to work on the quiz. Okay, so we have 10 minutes. Cover. So how do we model the parasitic capacitance for an inverter? So what's the cap here? Effective cap. So what's the effective cap here? What's the effective cap here? What's the effective cap here? So that's cox P, a half of cox P. And this will be cox P. And this will be cox N. This is a half of cox N. Why? Because these two caps have what effect? Mirror effect. So what's so C in here? So C in equals to all the caps being added together, right? So they are 2/3 of cox N plus 2/3 of cox P. So that's C in. If there are two inverters being shorted to each other like that, so you have seen this, a similar structure like that in a ring oscillator. They are looking from, looking into the two directions from this point. So you're getting actually two directions, and there will be an input capacitance over here and output capacitance over here. Okay. So looking at the output point, what is C out? Since we have C in already, so what is C out? There's two of them. Okay, so these are the symbols, but if you withdraw the circuit, it looks like this. This is one inverter. Why we have to model the one inverter in this way. So what are these caps and what are these resistors? So this is just one, okay? Why this and this are disconnected from each other? That's a gates, right? That's an input, gates. There's no DC current. It's just like dielectric material, gate oxide. So in that case, on the top, what is this cap? That's for the PMOS, right? So PMOS, so on the top, that's RP, that's the channel resistance of the PMOS, and channel resistance of NMOS. So what is this capacitor though, for the input? So these two being added together. And this will be this. So what about these two caps? So that's the output pin of the inverter. So on the top is cox P, and the bottom will be cox N. And if I have another inverter being shorted to the output of the first one, they just redraw the same thing here. Should I disconnect it or should I short it if I got another inverter? I'm just trying to model the two inverters here, right? So they are being connected in the middle. And got a first inverter, and for the second one, should I leave it a gap here or should I short them together? Short, right? Because it's shorted together here from the output to the input. So this is the same wire. Here's the same wire here. There will be a cap and one at the bottom. And then this one should be disconnected because that's a gate for the second inverter. That's the second inverter, okay? And when we are trying to calculate the time delay from this point, because these are the voltage nodes, right? That's one of the nodes. If you have a ring oscillator, you have a few others, and then close the loop. I'm going to show you why it oscillates later, but now just look at one node. This is one of the nodes in the ring oscillator. And when we're looking at one of the nodes over here, we have to calculate the time delay of it. So what are the caps and resistors involved? First, so what is TPHL? From high to low, one, two, three, four caps. So what are they? So what is this one? So what's the C total here? Yeah, just add all of them together, right? Cox P plus 2/3 of Cox P and Cox N plus 2/3 of Cox N. So eventually you're getting 2/5 of Cox P plus Cox N. Hmm? Oh yeah, so that's where, yeah. So I had the same question when I was a student. Okay, so now what's the best theory to explain that? Whenever we are looking at a transient signal, it's like AC. We only analyze AC, but not DC. So when we do AC analysis, or just looking at the varying signals, we just looking at the AC. So all the DC sources are actually AC grounds. So these are considered to be grounded. Not that one, sorry, this one. So if you ground all of them, they are in parallel. You just have a couple of caps in parallel being shorted to the ground. This is confusing. Why you can do that? Why when you are looking at AC only? Since in microelectronics too, if you go to graduate school, there will be another electronic class. There will be a lot of AC analysis for transistors and amplifiers. Whenever you are looking at the AC signal only, you short all the DC signals to the ground because you consider all the DC signals are just DC offsets, are not looking at the DC signal. And why you can do that? What's the theory behind it, supporting that? You can do it on a certain scope, right? But now we are doing analysis. You can do that because of superposition. That's why it's really benefit to do that a lot of times in the very beginning of the semester. It's not just here. For AC, DC analysis, you do them separately. But also in op-amps, I'm pretty sure you are getting confused for op-amps in circuit 1. Do you? I mean, so if you ground it, yeah, you have seen some of the circuits like minus 15 and 15, right? Which is fine. I mean, everyone can do it. So you can ground here. Definitely you feed it back and you have a V in. Does that work? Yes. Yeah, 15 minus 15, grounded. It's a virtual short. So what's the voltage here? Yeah. So this voltage will swing around where? Yeah, swing around there like that. If you amplify it, it's going to be like this. However, I never have like negative 15 volts on my board, right? It's usually I just have a ground as the lowest potential on the circuit, in the circuit. So it's going to be like this. So how do you want to do it though? Should I ground it? No. If you ground it, it's a negative feedback, so it's going to draw this voltage, it's going to drag this voltage to a voltage very close to 0 volts. And you get a voltage input, then what's going to happen? Yeah, so your signal, so here's 0 volts, for example. You want to swing your signal, forget about it. It got 0 as a DC offside, as a baseline. The signal will never swing to anywhere. Can you? No. 0 volts is the lowest potential in the circuit. You got an AC swing. It is able to swing upwards, but downwards, forget about it. It will never happen. So how do you want to do it here? Yeah. Lift it up to 2.5 so you can swing it. Make sense? Superposition. I mean, you're getting a 2.5, so this point will be permanent 2.5 DC. So we are thinking about the voltage input. How do you divide the problems? You got AC, you got DC. How to analyze it? It's like confusing people. Just do it separately, right? So the DC voltage is just being superimposed to this point. So any AC voltage is whatever is whatever is doing here, right? It's just like just bump it to 2.5. It's adding to it. That's how I understand it. Same theory, superposition. When we are doing this transient analysis, it's like a time varying signal. We short all these DC voltages to the ground. So that's why these caps are in parallel. That's a very good question. And so the C total here is in parallel. So all these are being added together. And for TPHL, what is it? Since we just need to know, like, because the TPHL is like 0.7 RC, so we know RC C already, which is the C total over here. So what is R? Sorry. Already very dirty, so never mind. What is TPHL? Which resistor is involved? High to low. High to low. It's dragging that to the ground. Rn, right? That's how you can pull it to the ground. So Rn is involved, Rp is not. So that's why TPHL is 0.7 Rn times C total. What about TPLH? Yeah, 0.7 Rp. They share the same C total. Okay? All right, let's do the quiz.